Good afternoon. I'm Rafal. I'm a software engineer on Google Play Console, and I work on Android Vitals.
Hello, everyone. So glad to be here. My name is Dario, and I'm one of the engineering leads on the Play Console, and I work on analytics. So who here likes one-star ratings? OK, that's very good. Because in this talk, we are going to show you how not to obtain any more one-star ratings, right? By using the tools of the Play Console and Android tools to make great apps. So we'll quickly go through why this matters. My colleague Richard in the previous talk, if you were here, already touched on this. So I will briefly skim on this part, just for those of you who weren't attending the previous talk. And I will introduce the Android Vitals and the concept of bad behaviors. And then Rafal will go more in depth into each single bad behavior and how to detect and fix them using both Play Console and the tools that come with Android. So first, let's discuss why you should care about this. The reason is because it matters on a number of fronts. Throughout this presentation, I will show you several dimensions that are affected by app performance. This one, for example, is ratings. So we analyzed the English reviews using machine learning, and we actually found some strong correlation between one-star reviews and stability and bugs. Namely, 50% of the one-star reviews mention something about stability and bugs. And also, we saw that 60% of our reviews praise the design and usability of an app. And it's not just only about ratings. The developers of Big Fish games actually saw a boost of 1.5x on the 30-day retention rate by focusing on load times and RAM usage. So Android Vitals is a large effort at Google to improve the stability and performance of Android devices. And as you probably saw earlier, we started by focusing on 3 performance areas, including stability, battery, and rendering. So stability is about making the app robust and reliable. So as we'll see later, it's all about making so the app doesn't crash or doesn't freeze for the user. Battery is about the impact that your app might have on the user's battery life. As probably you, like me, as a user of normal devices, get frustrated when you don't reach the end of the day. Your apps actually play a key role on that, and we will see later on why is that and how you can prevent your app from badly affecting battery life. The third performance area is rendering, which is about achieving the smoothness so that the users perceive your app of great quality because the rendering is like smoothly going at 60 frames per second. There are many more aspects. We will touch on that later in this presentation. But for now, we think that if you focus on these 3, you're off to a pretty good start in building a great app for your users. So once we identify the major performance areas, another big challenge is how to understand what is good and what is bad. This is not an easy question. For example, if I tell you, 2% of users experience slow rendering, how would you tell whether this is something important to fix or not? Well, we actually have more data on our side to make that call, and we focused on identifying what we call bad behaviors, which are the core metrics you should focus on to make sure that, and improve, to make sure that your app is of great quality. A bad behavior is an application habit that have a significant and lasting impact on device performance and user experience. There are 6 bad behaviors which we'll cover today across the 3 performance areas, and Rafal will explain what they are, how to debug them, and how to fix them. This is the Android Vitals dashboard. You probably have seen that already. If not, you can just head to the Play Console. And we worked through this part together to see what each section is for. OK, so before diving into details of bad behavior, let me touch again on a point that Richard touched on in the previous talk. In the previous version of crash reporting, users could only report a crash by acknowledging a dialog every time they were experiencing a crash or an application frozen. This was a tedious operation and also led to a very low volume of crashes. With Android Vitals instead, we actually ask the user only once whether they want to share their diagnostic or their phone with you developers and with Google. This typically happens at phone activation, and it's a very low friction gesture. This led in many cases to an increase of 100%, to increase 100 times of crash reports, certainly more than 10x for each app. Still with a pretty good coverage. All the devices coming from Jelly Bean on are covered, which should account for like 98% of the devices running Google Play services. I will now pass the remote to Rafal to speak about the bad behaviors.
Thank you, Dario. So let's walk through the bad behaviors we have in the console today. And we start with stability, crashes, and ANRs when the app freezes. For sure, you never want a single user to see any of them. So we define the bad behaviors in terms of percentage of users who experience at least one of them in a given day. It's equivalent to the crash-free metrics you might be familiar from Crashlytics. Most of you are more likely familiar with how to handle crashes. So today we focus on ANRs, when the app freezes and stops responding to input. This usually happens due to a deadlock, a blocking operation in the UI thread, or broadcast receivers taking too long to complete. ANRs are really disruptive to the user's experience. When ANR happens, the app is frozen, so you cannot typically use a crash reporting SDK to collect them. On the other hand, Android platform tracks them automatically, and they are available in the console without you having to do anything. When you navigate to Android Vitals dashboard, you can review the performance of your app. You can see how many users experience an ANR across app versions, devices, and OS versions. App versions with significant fractions of impacted users are highlighted and require your attention. From here, you can see the related ANRs in the ANRs and crashes sections, where, in addition to that, you can also review your overall crash-free and ANR-free rate. Android records ANRs almost instantly as they occur, and soon after that, within few minutes, they are available in the console. Newly introduced ANRs are marked with the app version that introduced them, and the impacted users column gives you a sense how widespread the issue is. For each ANR, you can access additional details, like impacted users and volume over time and across app versions, OS versions, and devices. For ANRs, you can also see the full thread dump that gives you the complete state of the application when the ANR happened. And similarly, for crashes, you can see the stack traces that contribute to the given crash. That should give you a good sense of what was happening on the user's device. The next step is to try to reproduce the ANRs locally. Android Studio 3.0 ships with Android Profiler that shows the real-time CPU and memory usage and network activity. As most commonly, ANRs are caused by slow operations in the UI thread or long blocking network calls. Let's see how we can use this tool to debug them. The CPU profiler shows the real-time CPU usage on the timeline, and the flame chart below shows which methods in the UI thread use up most time and become blocking. The network activity profiler shows the network activity on the timeline with how much data was sent and received and what was the latency. Here you can find the slow network calls and see in the source code when they originated from. How can we prevent ANRs? The Textbook recommendation for this is to not do any blocking operations in the UI thread and use async tasks instead. And if you enable strict mode, you can also cache accidental network and disk access from the main thread. Another common case are broadcast receivers taking too long to complete, or when they call go async and never call finish after. Those are very simple examples, though. You most likely do multiple parallel operations asynchronously or use helpful libraries like RxJava. However, the same recommendations apply. Be mindful on which thread the code executes on, and use the semantics of the library to ensure the code remains on the background thread. And finally, be mindful and watch out for deadlocks. ANR traces in the console will help you spot threads that mutually blocked each other. Is it worth fixing all the crashes and ANRs? Absolutely. We looked at apps with high crash rate in Play Catalog, and we observed that those apps have 30% more uninstallations in the first day than the more stable apps. Let's move to the next section, battery, which is a top concern. Android powers down CPU, radio, and other components to save the battery life. So letting the device sleep is very important. As a developer, you can keep the device awake using a wake lock. There are two types of wake locks. A full one, when the screen is on, that usually is used by games or video apps, and users have complete control over it. And the partial wake lock, when the screen doesn't need to be on, and it can silently drain the battery. So we define the bad behavior as the percentage of users who experienced a wake lock held for more than an hour. We called it a stuck wake lock. Android Vitals shows you how your app is using or abusing wake locks. App versions with significant percentage of impacted users are highlighted, so you can focus on them. In this example, we can see that majority of wake locks are below 1 minute, which is great for battery. However, there are some stuck wake locks which were held for more than an hour. Android Vitals dashboard also gives you the names of the wake locks. Due to privacy reasons, only names that appear in multiple sessions are shown. To make your wake locks debuggable, please use the standard names for each distinct wake lock, so you can find them here. In this example, the cleanup wake lock is acquired by the app to perform some cleanup task. The reason why we highlight wake locks is how dangerous they are. Last summer, we analyzed reports about bad battery days. A bad battery day is when the battery didn't last as long as usual. And we found that in 30% of cases, it was related to a stuck wake lock. So you should avoid wake locks if possible. They were introduced in early versions of Android platform, and now most of the use cases for them are better served with new APIs, like Download Manager for downloading files that manages retries and network changes. The sync adapter to sync app data with a remote server that also works in background and also can be tuned to perform the sync only when necessary or at a specific time of day. And Android can schedule multiple syncs together to optimize for battery. Job dispatcher from Firebase if you perform a background task. Jobs will be scheduled in the battery optimal way when the device is awake and connected to network. Or job intent service if you hold a wake lock to finish processing an intent. If you cannot avoid wake locks, remember to always call always call the release on them. Be very defensive in error handling around wake locks. Skipping this release call means a bad battery day for some users. You may not use wake locks directly in your app, but services or libraries you use may use them, and they will be attributed to your app. In this example, we see a wake lock held by location manager to obtain when the app obtains device location. So even if you didn't use any wake locks, you should review what wake locks are attributed to your app in Android Vitals. Let's move to next bad behavior about battery, wake-ups. They are used by Alarm Manager API to wake the device up outside of the lifetime of your application. Excessive wake-ups prevent device from staying idle and going to sleep. So we define the bad behavior as the percentage of users who experience more than 10 wake-ups per hour. Just like with wake locks, Android Vitals gives you the names of wake-ups you used. App versions with significant fractions of impacted users who experienced more than 10 wake-ups an hour are highlighted, so you can focus on them. A common pattern to perform a task at regular intervals is to schedule a wake-up and then use a wake lock until it finishes. This use case is better served by Firebase Job Dispatcher. Those jobs are scheduled in a battery-optimal way when the device is awake and the other constraints are met, like device is charging right now or on unmetered network. To save battery even more, we should schedule those jobs less frequently. And finally, let's talk about bad behaviors around render times. How long it takes for frames to be displayed on screen. It impacts the smooth and pleasure browsing experience of your app. Apps are rendered 60 frames per second. So each frame has to be rendered in less than 60 milliseconds. Otherwise, if a frame takes just 17 milliseconds, it gets dropped. Those slow frames will make users feel the app is stuttering. And if you skip multiple frames in a row, the app starts to feel unresponsive. And we found that 700 milliseconds is the threshold when the user starts to think the app is frozen. So we use these thresholds to define the bad behaviors. The slow rendering, when more than 50 frames are slower than 60 milliseconds, and frozen frames, when 0.1% of frames are slower than 700 milliseconds. You can see in Android Vitals dashboard how many users are impacted by slow frames or frozen frames. App versions with significant percentage of impacted users are highlighted, so you should focus on them. The dashboard shows the distribution of render times across app versions, devices, and OS versions. Additional metrics gives you a sense what might be causing the slow rendering. In this example, the slow UI thread may indicate that the app is doing too much work in the UI thread. To pinpoint exactly what's causing your app to drop below 60 frames per second, you can use Frame Metrics API. Then analyze the collected data produced by it to find the flows that take the longest to render in your app. Then try to reproduce those flows locally, and then in the systrace, you can find exactly what were the operations when the slow frames for that flow were rendered. Now back to Dario.
Thanks, Rafal. So as I mentioned earlier, the stability, battery, and rendering are just the 3 performance areas we are focusing on. But there are many more that that we believe are interesting and they should be addressed. So you should expect more of them coming in the future. Such as like up startup time, disk I/O, memory, excessive background work, and network. So check Play Console regularly to see how you're doing with the existing one, and also whether new bad behaviors are being introduced. Finally, if you want to dive even deeper into app performance, we recommend you to try out File-based performance monitoring, which is a new tool we launched at I/O in May. It has a bunch of cool functionality to instrument and track your app performance, be it network latency in the field or custom events. So to recap, we talk about app performance and how much it matters if you want to achieve a stellar app rating and also if you want to maximize user retention. It just leads to happier users. We introduced Android Vitals and bad behaviors, which are application habits that, when present, have a significant and lasting impact on device performance and user experience. We focus on crash rate, ANR rate, slow rendering, frozen frame, stuck wake locks, and excessive wake-ups. And these are bad behaviors were identified in the three main axes of stability, performance, and rendering. Rafal also showed you how Android Studio can help you address these bad behaviors and fix them, detect them and fix them. So we discussed all the new tools that Android Studio 3.0 offer to you. And generally also the Android APIs that can help you avoiding these anti-pattern in the first place. We hope you liked the session. We will be available in the speaker corner. There will also be an interpreter, so feel free to join us right after the session. Thank you very much.
Thank you.